Thank you. Cool. Thank you for coming to my talk. My name is Italo. I am from Brazil, actually, but I live in Berlin for a while, so it's not too far away. But I feel the cold still, so all good. Right, I am working currently at Lykon in Berlin. I'm the head of technology there. Previously, I was working at HelloFresh and also N26, mainly doing things in Go, but especially working site reliability engineering. So for a bank, that's quite important, like reliability is basically everything. And for a health company like Lykon also, you cannot mess up. So basically what I want to talk today about is how can we design better systems? How can we design systems that are ready to handle unexpected things to happen, right? As you know, we work in a distributed system world. Like today, it's really hard to think about a solid system working by itself. So because of that, I'm also a very huge fan of mission critical systems. Like if you think about airplanes, right? Everybody here probably already flew one of these. And just to put into perspective, in 2019 alone, we had 39 million flights going on, right? It's quite a lot. It's quite a lot of flights. Unfortunately, out of those, 8 result in a deadly crash, which results in 233 fatalities. Does anybody here know how many of these 8 deadly crashes were caused by a software failure? At least 2. That's good. 3. Okay, that's good enough. We can make a bet. Reported by the FAA, it was basically 1, right? Like, which is the 737 MAX case, which probably most of you already know. So the 737 was, well, it was a design error. I'm not here to say which person had a fault on that, but it gives us perspective. It's a very solid system, although it failed, but it's a very solid system. And that was designed in 1993, this system here called ELMS, which is Electric Load Management System, where software industry took a lot of the learnings from the electronic industry, basically. So a lot of the concepts that I'm going to talk about here were implemented in this system in 1993, and they were even designed way before that. They were designed way, way before that, in 1960s or so. And the main thing about airplanes is that failure happens all the time. We just don't see it. That's the thing. You're probably flying there, all good, all nice, but you don't know that actually the captain knows that there is something failing and you're comfortably there because it was designed to fail. It was designed to handle these failures and you can land safely. So the system was designed to keep the essentials running. And if you think about your software on a day-to-day basis, can your software only running its essential resources? And that's how we put into perspective these kind of things. And I like this quote quite a lot, which is, resilience is a requirement and not a feature, by Liang Wu. I think I pronounced it properly. And you know, like, especially in my case, when I was working before in a bank, resilience was one of the requirements instead of a feature. But even before that, like in previous experience, I had to convince POs that actually makes sense to implement circuit breakers or to implement some sort of resilience in case something fails. And that was quite a challenge. Like, try to convince people that very technical things, you have to be very good in explaining why you're doing such things. So today I want to talk about a few things, which is latency control, load shedding, isolation, self-healing applications, and traffic control. So those are a few of the strategies that you can apply in your day-to-day work and probably in a few of your systems, and to ensure it's a little bit more reliable in case something fails. And let's start with latency control. Timeouts. Timeouts are probably the most basic thing that you can implement right away that will give you some sort of safety in external calls, external dependencies that you might have, or even if you're running a web server, you probably want to set your own timeouts just to make sure you're more resilient and you're going to avoid this kind of cascading failure. So there are 2 types of timeouts. One is called client timeouts. The other one is server timeouts. So what does a client timeout look like? in a very, very simple setup, this is a client timeout, right? You have the HTTP client, and you set the timeout right there. And that basically says if your request does not finish in that time, it's going to cancel the request, right? It's going to stop, it's going to cancel, you're going to receive an error, and you can treat the error, you can handle the error. You can go a little bit more fancy and say, okay, let's configure the transport layer. Let's make sure we set timeouts on the dial layer or on the keep alive, and TLS handshake even. So you can go really deep here. There's even more configurations than this. And these are arbitrary numbers. You have to figure them out by looking at your metrics probably. But these are the defaults that I normally put in my systems. So yeah, this is a very simple thing. Now, in Go 1.13, we have a new thing right there, which is called HTTP new request with context, where you can provide a context to the request. So if you see in the lines above, you're going to have the HTTP client, and I'm not setting the main timeout there. The reason is because you can now pass a context with timeout, and that is going to trigger the cancellation callback, basically. And then you can handle the Go routines properly if you have to. So this is simple client timeout working, which is pretty useful, and you can handle the timeouts and like call something else in case that happens. On server timeouts, we have a different setup. We have a setup where we can set the read timeouts, the write timeouts, the idle timeouts, and the read headers. So that's super useful for the browsers in case your server starts to hanging or you cannot handle many requests. So you basically set those timeouts, and you get a little bit of more reliability and error handling into that. Now this one is a big one. Who here uses circuit breakers on a day-to-day basis? Cool. Not so many, but yeah, because it's not so trivial to implement, but it's trivial to use. So basically, what is a circuit breaker? A circuit breaker is a way to, it comes from electronics again, it's a way for you to basically notify when something is actually failing. So in this case, we are saying here, like, we're going to do requests to an external API. And this external API can fail 3 times. That's basically what we're saying. So it can fail 3 times. If the status code is bigger than status bad request, and this can be any kind of check you want to do, we're going to open the circuit. So if you had the opportunity to study electronics a little bit, if you open the circuit, there is no electricity going through. Same thing happens here. Basically, well, not with electricity, of course, but basically the request stops going to the server. So this is super useful when you have a server that is overloaded. So if your server is overloaded, you put a circuit breaker on the client side, you're basically saying here, okay, the server failed already 3 times. I will stop calling it, and then I will retry to call later, right? Just to see if you can handle more requests later on. This library, GoBreaker, comes from Sony, which is pretty reliable, it's pretty good. There is a standard in the industry from the Java world called Hystrix, which is not supported anymore, but it has a great paper about circuit breakers, which is super useful to understand. And it gives you something like this dashboard here, which shows all the circuit breakers you have in your code. And it's going to show if the circuit is closed, which means request is going through, or if it's open, which is then a problem, right? Then that means, well, your external dependency is actually not responding anymore, and I stopped calling it. But circuit breakers by themselves are not very useful. Like, okay, it's going to show you my circuit is open. How do I close it again, right? Like, otherwise it's going to stay open for a while. That's when retries come into place. You have to have a retry. Otherwise, you have to manually go there and then restart your service. So the circuit breaker restarts the memory allocations and everything. So with the retries, and here I explicitly have the Hystrix example. Basically, you can have multiple retries strategies. You can have linear strategies, which is, okay, my server failed, or the external service that I'm calling failed. I'm going to retry every 2 seconds, and then try again, try again, try again, try again. Even though that's sometimes useful, probably your server is not going to respond in 2 seconds, or 4 or 6. You probably want to wait a little bit longer. For that, you have the exponential backoff, which is it's an interesting strategy which uses exponential algorithms, and then basically it retries after 2 seconds. And if it doesn't work, okay, now I'm going to wait this times 2. So it's going to, in 6 seconds, it's going to call it again, so on and so forth, up to a threshold where you're going to say, yeah, this server is not responding anymore. Please use my alerting systems to notify me, basically. So backoffs are super important. Like it's the way for your circuit breaker to actually start working properly. On the load shedding area, this is a much easier thing, although we don't do it much in Go, and we shouldn't be doing this on our apps, unless you're doing client-side load balancing. So load balancing is normally done for us by someone else, either Nginx, or if you use a service mesh will do it, or AWS, you have ELBs, you have AOBs, and load balancing is the most common load shedding kind of thing, right? You have service B, you have 3 replicas of that service, and the requests are being load balanced by an algorithm, which is by default in Nginx, I think is round robin, but I'm not quite sure. And that's great, but what happens if one of those servers or one of those replicas, they go down? How does the load balancing scheduler knows, okay, one is down, I will not route traffic to that? For that, we have the Outlier service host detection, which is another strategy that basically identifies, okay, one of these are not really performing really well, I will not route traffic to it. That's basically what it does. So it keeps like this, and, whoops, sorry. It keeps doing this. That's super useful, but it's transparent for Go developers normally because we don't do this unless you're building a proxy or you're building a load balancing algorithm. If you use the Go proxy, reverse proxy built in the HTTP library, it does have round robin there. So it load balances across your different targets. So it's pretty useful. In the isolation area, anybody ever heard about bulkheads? No. Okay. Bulkheads come from this big ship, Titanic. So the Titanic, as probably most of you know, went down, I think in 1912 or something, because of a failure of design. So you know this line, this image is horrible, I know, but look at the lines. Look at this yellow lines. I think this is yellow. Look at these yellow lines. The water starts filling up into those, right? That is because that thing there is called bulkhead. It's a contained kind of resource for your ship. And this came from the naval industry. So the bulkheads in the Titanic, they fail because I don't know if it's called architect or design, I don't know. The person that actually designed the ship forgot that when the water goes up in those 4 containers over there, the ship cannot handle the weight anymore and actually cracks, and that goes down. And the water was going up and going to the next container and next because there was a small gap in the top for the air to pass through because they didn't have a way to pass the air through I don't know, through pipes or something. So the water went up, and then the ship basically sank. So the bulkhead algorithm or strategy is also implemented in the Hystrix library. So if you use the Hystrix pattern, you can basically do bulkheads. What does that mean for Go? That basically means that in Go, the bulkhead works with a sync pool. So you can have a sync isolation of a bunch of Go routines that actually calls the same servers. So if you're calling concurrently many services and one of them stops, your whole application will continue working to call the other ones, but one of the Go routines will be blocked because they're probably hanging the request there. But at least it's isolated. So the idea of bulkheads is isolation. That's where the idea comes from. Self-healing applications. Self-healing is super important. Health checks are what makes your load balancing algorithms basically work. And there's a few libraries in Go that you can use for that. This one is from InVision, the InVision app for designers. And it's a pretty useful way for you to standardize health checks in your application. What you have to do is basically create a checker. So you have, let's say that you have a database, right? In this example here, we have a database. And right here, we have 2 dependencies for my service. One is the Google, for whatever reason, and another one is the DB. But if you look right here, we have one saying fatal, one saying false. That means basically if my database goes down, my app does not respond anymore. The other one says if Google goes down, I don't care. My app is still responsive, but it's not really working well. So maybe a few endpoints or a few features of my server are not going to work. This basically shows this. Here I have an example with AMQP, so this is Rabbit. But if you look at there, we have a 200. So that means everything is running OK. So the load balancer algorithm can still route traffic to you. If things are not so good, but you still can work, you're still going to see a 200, because if you reply 400 to your load balancer, it's going to kick you out. But it replies 200, but then it says, OK, RabbitMQ is not really working too well, so maybe I should alert you about it. And that's fine. Otherwise, if things are really bad, you have a 500. And that tells the load balancing algorithms, OK, kicking me off. I'm terrible. Or if you're running Kubernetes, then it's going to restart your container, your pod, basically. So this is a super interesting library, and also standardizes the way you see metrics. So you can put this in Grafana, for instance, and then start monitoring all of that, which is super useful. Which brings us also to the outbox pattern. I don't know if anybody here uses Kafka, Kinesis, Rabbit, anything like that. OK, good. A lot of people. Have you ever thought about what if Kafka is not there? What do you do with your messages? Yeah, it's tough, right? Yeah. Kafka should be there. If you have a nice cluster, well set up, multi-region, probably even multi-AZ, and so on and so forth. But what if it's still not there, right? Like, what if Rabbit is not there? I have a lot of stories with Rabbit that are not really good, where Rabbit was not there because we didn't configure properly, let's put it like this. And the example of the outbox pattern is exactly to handle this kind of things. It's more for producers than actually consumers. Because consumers, all right, if Kafka is not there, well, fine, my consumer is there. I can probably just restart the connection after a while, and the world will not stop. But if I cannot produce a message, and my system is heavily based on messages, so it's event-driven, then I have a problem. And then if Kafka is not there, or Rabbit, or anything, I have a problem. The outboxer patterns say, OK, I will store all the messages into my primary data store. That could be your Postgres instance. That could be your MySQL instance, or any other things. And then I'm going to have a sender, which could be another Go routine, or could be a cron job, or whatever you want, that basically will try to send to Kafka. If Kafka is not there, that's fine, because your messages and your transactions are still being completed into your primary data store. Now, if your primary data store goes down, you probably have a bigger problem to deal with than just messages, very likely. So in Go, we have a library like this that I developed, which is for the outboxer pattern, which basically I say, OK, I have a Postgres instance as my primary data store, and I will have it like there. My event stream is then set up right there. You can have Kafka, you can have Kinesis, you can have RabbitMQ. And then we have this check interval, which is how often you want to check the health of Rabbit or Kafka, right? If it's not there, I won't even try to send it. And then we have this cleanup interval, because if your system needs to handle a lot of throughput, then basically you have to deal with a lot of messages in your primary data store, and then you have to shard that data, which is, it's a little bit tricky. So you probably want to clean up after a while, especially if you use Kafka as your event stream. So it's quite good. So if you want to check it out, it's going to be here. And it's an interesting library. Cool. And traffic control. Right. So we have rate limiters are probably the one that is most famous. If you ever develop a gateway, you probably dealt with rate limiters. But even if you didn't, internally into your apps, imagine that you have many services, and a lot of them are calling your, I don't know, authentication service, for instance, which has to deal with a lot of tokens, so on and so forth, because we're not using MTLS. So that's basically the reason. And let's say that you're not dealing with it properly, and then your server cannot handle requests anymore. So you can rate limit, you can do quotas, you can say only a specific request can go through it, and this basically helps. Rate limiting in Go is, of course, super easy to do, unless you try to do distributed rate limits. That's when things start getting a little bit tricky. When you have a single instance of your application, a single replica working, it's easy to have an in-memory store and all good. Or if you don't care too much about consistency across those three for your rate limiting, all good. If you have to deal with distributed rate limiting, then you need some sort of like Retries or something outside to actually keep increasing the counter, and you have to make sure that doesn't bring you down as well. So watch out for that. All right, so we've been through latency control, load shedding, isolation, self-healing, and traffic control, which is a lot of things. Try to imagine implementing, and I just scratched the surface. If you go very deep into these things, it starts getting very heavy, the amount of things that you have to think before you even start developing your business case into your code. So with one service, that's all fine. With 10 services, that starts feeling the pain here and there. When you start reaching 100 services or 1,000, then you have a problem. You probably don't want to replicate this to all your services. If you're using Go, you're still going to suffer. If you change the library, or if you want to keep the contract across all of these 1,000 services, you're going to have a problem. For that, we have service meshes. Anybody use service mesh today? Sort of? Sort of. Okay, it's good enough. It's good enough. All right, a service mesh is basically running a sidecar, aside your application, right, side to side. And if you use Kubernetes and Istio, for instance, which is a nice marriage between those two things, basically you're going to have your proxy or a sidecar running as a proxy, right? So every request that comes out of your application is actually going to trigger, it's going to go through the proxy that will implement a few rules here and there to deal with Istio. So I can show you, hopefully this will work. Hold on. Can you see this? Yes. Okay, good, good. Can you see this? Beautiful. All right. So let me see if I can show you how a secret breaker is in Istio. Let me make this a little bit bigger. All right. Let me close this. All right, there we go. So here we have a secret breaker done in Istio, which is a very simple way of configuring secret breaker. So you have an outlier detection right here, and then you have your configuration of this secret breaker is kind of like just a demo, really, because you don't want to handle one request concurrently in your application. But basically, you can set up how many HTTP requests you want to handle, what's the threshold if you want to call an external service, when should I fail, when should I not fail, and you can configure all of this in this traffic policy, which is very useful, very handy. That means in Go, you will not need to code secret breakers for all your 1,000 services, which is sort of good. Now, you have to take this with a little bit of be a little bit careful, because, well, service meshes have the pros and also have the cons, right? As everything else. So you have to really see if it's a good fit for you. But just an example here as well, we have the retries. So you can specify how many retries you want to do per host and how many times you want to, retry and then trigger the secret to open or close. And you can also implement timeouts. So, whoops, timeouts. There we go. So you can also implement timeouts, which is the client timeout part of it. You can also implement the server timeout part of it, all in Istio, which is super cool. And that means you can standardize a little bit better across multiple services. When you reach a size of, well, not size, but the amount of services you're going to have in your architecture, you probably don't want to do that by code. You want your SRE team or ops team to start taking care of all of these as well, together with your dev team, of course. And hopefully this will work to come back. Yeah, cool. So nothing that I said here actually works without observability, right? So observability is basically the base thing you must have in your system to be even able to figure out what are your thresholds, what are your timeouts, what are the amount of requests that you can handle, so on and so forth. And metrics are the most basic things you must have in your application. And there is a very nice standard which is cross-language. So if you come from the Python area or the PHP world or Java or Go, we have something called open census. Don't know if anybody uses here, but open census is basically trying to standardize the way you produce metrics back to your external services, and how you do tracing, how you do logging even in the next version. And yeah, it's super useful. So here, as you can see, we have some built-in HTTP metrics, like client send bytes, so you know the amount of bytes, you know amount the round trips, the latency, and so on and so forth. And I'm exporting to Prometheus in this example, but I could export to Datadog, I could export to New Relic, I could export to anywhere that I like, StatsD even if you want. So it's super useful, and it's standardized across your application. So if you change your exporter, your code will remain the same, basically. And it will produce a few built-in metrics. It has some nice dashboards that you can actually play with. It sets up a few alerts as well. So it alerts you on, I don't know, OpsGenie or PagerDuty, whatever you use, which is super useful. Distributed tracing, it also comes with distributed tracing for Jaeger, if you use Jaeger, super useful as well. Or if you use something else, like Datadog for tracing, it also supports that. And it's standardized across your application, and even across languages. When you work in a bigger company, probably you have teams dealing with Python or Go or PHP, and then you want to standardize metrics across those languages. That's basically what you need to do. And in the recent notes, Open Census and Open Tracing, which is the two standards, are joining forces. And finally, they are doing Open Telemetry, which is the new thing coming up right now, which is going to be a new standard for not only for the Go industry, but also for the whole telemetry industry. So Prometheus people are here, Grafana people are here, basically, joining forces into creating the Open Telemetry specs that will be distributed across all languages, all bigger languages. Yeah, so here are a few links in case you want to check it out. The code there, and you want to see how to configure a secret breaker in Go. You can go to these slides here. And the coffee shop example there is just because I love coffee somehow. So there is a system running with Istio, and you can actually try it out. And if you run Istio, you can inject a few failures into the system and see how your system reacts into it, which is super cool if you jump into Kubernetes world and you want to try out how healthy your system is. You can inject failure into it with Istio, which is super nice. Yeah, I hope this is thank you in Russia. This was a friend of mine that wrote it. Is it? Okay, we're good then. Thank you.
Thank you. We're ready for questions.
All right, we have a question.
In your Kafka example, for me as an outsider, it seems like your solution to dealing with Kafka going down is to put another Kafka in front.
No, not quite.
But
no.
Could you explain a bit more what the thought behind it is?
Absolutely, yeah. So the Outboxer standard actually is introduced by Microsoft, and basically it's not to put another Kafka, otherwise kind of loses the point. It's to have another data store, right? So you have your, let's assume that your primary data store is not actually Kafka, you have a Postgres running aside. You're going to put all your messages into Postgres, basically. And then you're going to have a Go routine or something else, a scheduler, sorry, a cron job, that's going to get that in a scheduled way. It's going to actually send it back to Kafka in case it's not there. You can handle it. And once it's back, then it starts putting the messages into there. That's more or less the idea. Yeah.
Hi, thanks for the talk. Do you have a code example of the bulkhead practice? Because I don't think I understood what the bulkhead actually meant in practice.
Absolutely, yeah. You can actually check into the Hystrix library. So the Hystrix library in Go, it's the implementation of the Hystrix pattern, which is a paper developed by Netflix. And there they basically know how to do, or they show you how to do Bulkhead in Go, which is using essentially a bunch of Go routines and isolating them. So in case one of the Go routines stops because your server is hanging, the other one still works, so you can still call the services in the other ones, so your whole app doesn't stop. If you don't implement bulkheads, and you use the normal HTTP request, sorry, the HTTP library, even worse, if you use the default HTTP client, your whole system will stop, because it will hang, so the request will hang. So that's basically what the bulkhead does. So you can check on the histories.
Okay, questions? No? Okay,
Cool.
thank you.
Thank you so much.